We're all familiar with gravity, that magic force which pulls everything down to the ground. But what is actually causing things to fall down? Stay tuned and you'll find out. You're probably familiar with Newtonian mechanics, which describes gravity as a force of attraction between all objects with mass. However, this doesn't actually tell us why objects with mass attract each other. To answer this question, we have to look towards our current best theory of gravity, which is general relativity by the very famous Albert Einstein. According to general relativity, we actually live in a 4D universe called space-time, where the fourth dimension is time. Every object has a trajectory not only through the three spatial dimensions, but also through the time dimension. In the absence of gravity, an object at rest moves only through time in the forward direction, which is depicted as upwards. A massive object distorts space-time such that the trajectories of nearby objects now curve towards the massive object. While this is how general relativity is usually explained, it is confusing because we cannot visualize a four-dimensional universe. It also forces us to think of time as a spatial dimension, which is not how we actually perceive it. A better way to visualize general relativity is to instead show how the geometry of the spatial universe changes over time. To understand how changes in the geometry of the universe cause gravity, let's first visualize an empty universe with no mass or energy. The universe is depicted as a Cartesian grid where every point in the grid is equally spaced from its neighboring points, meaning there is no distortion. This universe has a Euclidean geometry, much like a flat piece of paper. Now let's add an object with a small mass to the universe. Notice that the grid is more distorted, meaning the points are closer together in the vicinity of the object than in the rest of the universe. Also notice that the creation of a mass caused ripples to appear. More about that later. Something interesting happens when we increase the mass of the object significantly, which increases the distortion of the universe. Notice that the distortion causes the entire grid to be pulled closer and closer towards the center of the mass. This process continues over time, with more and more points in the grid being pulled towards the center. Now let's repeat this virtual experiment with a second object that has a small mass. Initially, this object is stationary. When we introduce the large mass, the object appears to move towards the large mass following the movement of the grid. Even though the object appears to be moving, it is actually stationary relative to the grid because its coordinates are not changing. The object stays on the same grid point that it was placed at initially. The apparent movement is due to the local distortion in the geometry of the grid. What this means is that the object does not feel its own movement and does not experience any force being exerted on it while it is in freefall. On the other hand, if the object were continuously accelerating through the grid towards the large mass, it would be able to detect its own acceleration and hence movement. The apparent movement of the object continues until it reaches the center of the large mass. We don't see this happening in reality, however. We don't keep falling through the ground until we reach the center of the Earth, which means this explanation is incomplete. The reason objects don't fall through the ground is that gravity isn't the only force at play. The atoms and molecules making up the Earth repel each other and prevent the Earth from being compressed below a certain size. This repulsion force also prevents objects from falling through the ground. It is the balance between gravity and the repulsion force, which is actually the electromagnetic force, that allows a stable planet to form. If the electromagnetic force is too strong, the planet will disintegrate. If the gravitational force is too strong, the planet will turn into a black hole since its surface will no longer be able to stop matter from falling towards the center of its mass. The reason why we stick to the ground is because the surface of the Earth is constantly pushing us upwards, preventing us from falling towards the center. This is actually equivalent in effect to a continuous upwards acceleration. To understand why, let's draw a circle representing the Earth. Notice that even though the Earth appears stationary, the grid coordinates along the surface are constantly changing. The surface of the Earth, and everything on it is actually moving through the grid. On the other hand, objects in freefall are moving with the grid but are not moving through it. This seems like a mathematical trick. Surely the ground is not accelerating upwards. That's ridiculous. As strange as it may seem, this acceleration can actually be measured with an accelerometer, which is a device that measures acceleration. If we place an accelerometer on the ground, an upwards acceleration is measured. On the other hand, no acceleration is measured when the accelerometer is in free fall. How an accelerometer works and why this happens will be explained in a future video. Now that we've covered gravity, let's take a closer look at a related phenomenon that we observed earlier in the video. Earlier on, we noticed that when a mass is created, a ripple forms that travels outwards through space. Ripples also form when a mass is destroyed or accelerated. These ripples are gravitational waves, which were detected for the first time in 2015. A gravitational wave is a distortion in the fabric of space-time that travels at the speed of light in a vacuum, much like an electromagnetic wave. However, unlike electromagnetic waves, gravitational waves barely interact with matter, which makes it much harder to detect them. They are not absorbed or scattered by matter, however, they temporarily alter the geometry of space-time, which causes distances to contract or elongate. Notice that as the waves pass, the horizontal distances between the objects contract, causing them to move closer together. At the same time, vertical distances remain unchanged. To end off, we now know that gravity is caused by a curvature in the geometry of space-time, which causes space itself to move towards the center of massive objects. Thank you for watching, and I hope you found this video interesting.